So in this video, we're going to go ahead and take a look at some examples of how to graph a piecewise function given the equation already here, and then also look at how to evaluate functions, piecewise functions at particular values. So the first thing you have to understand is it would really help to sort of sketch, like, well, what is this? This is a line starting at 1 going downward. So it helps to sort of just get an idea of what the picture of these looks like before we put them on a graph paper. If I think about this graph, this is a graph starting at the origin going upward with a slope of 1 over 2. So now that I know that, there are two ways to do this. The first way that some students will do is they will go onto the graph and actually graph exactly what they just did. So they'll go to 1, they'll go down 2 and over 1, and my advice would be to fill the entire graph paper up with those dots being produced from either the slope or later when you have a parent function. So that is that function. And then if I do the green one would start at the origin and go up 1 and over 2, up 1 over 2. Just a little review of how slope-intercept works from Algebra 1. So now I have these two graphs that I sort of modeled here on the graph paper. And now what I want to do is I want to take my eraser and erase anything that's not in this domain. But before I do that, I want to think about what this domain is saying. This domain is saying that you want to use a solid dot and graph everything that is before -1 on the x-axis. Where this graph is saying use an open circle and graph everything that is after 2 on the x-axis. So when I think about that and I get my eraser out, I want to go to -1 on the x-axis. And I want to basically keep only these two dots and erase these dots because they are the dots that are out of this domain. And for this one, I want to go to 2 and only keep the ones that are greater and erase these dots that are not in the domain. Then I would want to come back and actually sketch the graph in here. And just be careful when you go to here. So like this part, when I sketch that part, I'm going to need to be careful because it currently has a solid dot from when I recorded what that line looked like over the entire interval. So I'm going to want to go back and just make sure that I erase that dot and actually make it open circle. So the other way, when you get a little better, is to do it like this. So that's a great way to start, but as you get a little bit, and some students just like one way versus the other. The other way is to figure out where this point actually is. So the way you would do that is you would take -1 and you would plug it into here. So if we plug -1 into this function, we would have positive 2 plus 1, which would be 3. So what you would do is you would graph that point as a solid dot, and then you would use the slope in reverse because it's going to the left, so you'd go up 2 and then -1 that way. Remember, the slope can be down 2 and over 1 as for that, but it could also be up and then back because this is a negative, but this is also a negative, so that would work. And so to do this one, you would put 2, so you take 2 and you would put it into this function. So if I plug 2 into it, I would have 1/2 of 2, which would be 1. So I would take the point 2, 1, and I'd graph an open circle, and then I would use the slope up 1 over 2 to graph it. So you can go directly to this graph, or you can subtract it. All right, let's take a look at one that has a little bit more parent functions in it. So to do this, we're going to do the same thing. We're going to give a little sketch of, okay, well, what does this look like? This is an absolute value going downward. It's going to be a V somewhere on here. This graph right here is a horizontal line. Keep in mind that you really can't have vertical lines with piecewise functions because this is y equals 3, which is a horizontal line. And then for the last one, we have a quadratic, and it is going upward. So I'm going to go to, and this is where we have to be careful, you have to make sure you also know where the vertexes are. So this problem right here has a vertex of 0, 0. I don't really care about the vertex for the horizontal line, but this one has a vertex of 2, 0. Remember, h is always opposite. I see a negative. It actually is going to be graphed at positive. So then I'm going to go to 0, 0 on my graph, and I'm going to fill it up with the dots that this will be. And this might take some students longer than others. So some students might have to go 1, 1, 2, 2, and then -2, 2, and then multiply by -2, and they will end up doing this, right? So this one that's here will be here. This one that's at 2 will be at -4. So you might have that might take a little longer for some students. Some students might go directly to these dots, but then you need to make sure you go back and erase the practice ones. So we started at 0, 0. We were supposed to go to 1, 1, but it was multiplying the output by -2, so it went 1, -2. Instead of going 2, 2, we multiplied the output by -2, so 2, -4. We'll come back and deal with the domain in a minute. So for the horizontal line, we would just fill up the entire graph paper with 2's, right? So we have 2's all the way across here. Make them as horizontal as you can. All right, and then for the last one, for the quadratic, we are going to go and graph that one at its vertex of 2. This one's just a normal quadratic, so 1, 1, -1, 1, 2, 4, because square root 2 is 4, then -2, 4. Now, if that's too many dots for you, just make sure you draw lightly and make sure you erase carefully. So now we're going to go back and we're going to understand what this domain is saying. Again, it really helps. It really helps to understand that when I do this, I want to keep a solid dot here. And notice that I'm labeling the problem before I'm actually doing anything on my graph. That's an open and then a closed circle, and then this one will be open. All right, so now I'm going to go use my eraser, and I'm going to go to my absolute value graph, and I want to keep things that are left of this dot. So at -1, I'm only going to keep this. I'm going to go back and erase these because they're to the right. For this graph right here, I want to keep things between. Remember, double less than signs and notation in mathematics means between. So I want to keep the one from -1 on the x-axis to 2. So anything that's not in between -1 and 2, I'm going to erase. And then for this one, I want to keep anything larger than 2, which is actually at the vertex. So I'm going to erase these pieces. And now all of a sudden I have a nice cleaned up graph other than one little thing. So if you want to, you could, make those open now. I like to kind of wait till the end and as a double check, so I always check it. So this was an absolute value, and it was headed down this way. This one right here is a horizontal line, and this one was a quadratic. Okay, so now I'm going to go back and erase the ones that need to be open. So that one should be open, and this one should be open, and I'm going to make sure that I do that. And of course, that's just your preference. If you want to make this open before you start, you can. My preference is to do it when I do it, just to double check to make sure I have it right. So it comes out looking like you did a whole lot of math there, but in fact, what you really did was just graph 3 graphs and erase pieces of it. The other way, again, would be to put this value in here. You have -1. You put -1 into the absolute value, it would be 1, and then you would get -2. And then you would graph the absolute value from there using that. This one, if you put stuff into a horizontal line, remember, you're just going to get 3 as the output. So you put in -1, you'll output 3. You put in 2, you'll output 3. And you would just connect the dots, open, closed. You put 2 into here, you would get 0. 0 squared would be 0. So you put 2 in here, and you would square that and get 0. And so that point corresponds to here, and then you would graph the rest of the square using the key points. So that method that I just showed you there is very helpful when we talk about the evaluation portion. So what I did was I took these graphs and I just wrote them down here. What if I didn't have a graph? How would I evaluate it? And the way you would do that is you would take -1 and you would plug it into the domain first and see if it's valid. So if I take -1, is -1 less than or equal to -1, or is -1 a greater number than 2? So it's true here, and it's false here. So you would not do this problem, and you would only do that portion. So you would have -2 times -1 plus 1, and then you would just evaluate that using Gelmdas. So you would have 2 plus 1, or 3. So to take a look at the next portion, again, you just kind of have to start that process over. So to take a look here at 13, where would 13 go? Well, you come up here and you say, well, is 13 less than -1? The answer is no, it is not. Is 13 a larger number than 2? Yep, sure is. So I will evaluate this problem with this portion of the function. So I would have 1/2. I inputted 13. So that would give me 13 halves, which you just can just leave it like that. I don't need to know that it's 7.5. In fact, if you say 7.5, it makes it a little more obvious that you're using a calculator, and basic skills like that, you don't need a calculator for. So what happens with 0? Well, when I do 0, I want you to show you what happens. It's actually not valid in either statement. So is 0 a smaller number than -1? Nope. Is 0 a greater number than 2? Nope. So this problem does not exist. It has no output value. It does not exist. Why is that? Well, if we go back and look at the graph, remember, I'm trying to evaluate this part of the graph. There's nothing in there. So you can see it very easy visually, but algebraically, sometimes it gets a little bit confusing why it comes out to that. All right, let's take a look at the other one. Again, it's the same problem as above. It's the same thing we had here, graphing. I just, cover the graph up. Let's see what happens when we try to evaluate. So when I try to evaluate g of -1, again, where is it valid? It would be valid here because -1 is equal to, less than or equal to this. So you would just evaluate that using the absolute value. Remember, the absolute value of -1 would be +1. So this comes out to 2 times -1. So I'm sorry, I just said it comes out to +1 and wrote the wrong thing. Let me fix that. So it comes out to 1. So you get -2. And of course, you can see that on the graph. I mean, if you want to go to 1 and look down, the problem is, what if you don't have the graph? That's why I'm showing you the evaluation algebraically. So to do 0, where is 0 valid? Well, if I take 0 and try to put it in here, is 0 less than -1? Nope. Is 0 between -1 and 2? Sure is. So I'll put 0 in this portion. And remember, while evaluating a function that is only one number, the output is always that number. That's what creates the horizontal line, because you're always getting 3. So that's why you just get 3 when you plug it into that horizontal portion. So I put 2 in here because the question is, well, where is 2 valid? Because the 2 is actually here and here, but it's only valid where it equals it. So I would not use this to evaluate 2. I would use this one because it has the equal sign. So this one is also just equal to 3. So then the next question is, okay, what happens with the last part? So, some students, when they see this, they don't quite understand that I'm examining the domain, right? So I'm ignoring these. I'm ignoring this. And I'm coming over here and I'm saying, is 10 a smaller number than -1? Nope. So not doing that one. Is 10 a number that is between -1 and 2? Nope, that doesn't make sense. Is 10 a number that is bigger than 2? Yep, sure is. So now I put 10 into here. So what I've been doing here is I've been figuring out which portion of the function to select. And then once I know, I can then evaluate what to do with the numbers. So g of 10 comes out to 64.